Okay, so we have been looking at Trimmer's vertical bracket equation, and here we know that if we have a scaling for different forces, then we can find how the scaling is going to work for acceleration, time, and power to volume ratio. Trimmer's vertical bracket notation. Okay. So, here if we know the scaling for force, say force F is scaling as L1, L2, L3 up to Ln, then we can find the scaling for acceleration. Scaling for acceleration is going to be L to the power minus 2 minus 1 L to the power 0 L to the power n minus 3, and similarly the scaling for time is going to be L to the power 1.5 L to the power 1 L to the power 0.5 to L to the power 4 minus n square root, and the scaling for power to volume ratio is going to be L to the power minus 2.5 L to the power minus 1 L to the power 0.5 to L to the power 4 minus L to the power n minus 2 divided by square root of L to the power 4 minus n. So, that is how the power to volume ratio is going to vary. Now, what we see here is that if force scales as L to the power 4, then the time will scale as L to the power 0. So, for centrifugal force, magnetic force, where force is scaling as L to the power 4, time will be independent of the length scale. Okay. So, if you consider example of centrifugal force and magnetic force. So, here the force scales as L to the power 4, and in that case time would scale as L to the power 0. So, what it means is that the time becomes independent of the length scale. Okay. So, this is contrary to our belief that small things tend to be faster. Okay. So, here we see that the time is not going to change with length scale. So, that is one observation here. So, the time is independent of length scale. Okay. So, that is one important observation. The second observation is that the maximum scaling is going to be for mass moment of inertia, where it is going to scale as L to the power 5. Okay. So, for mass moment of inertia going to scale as L to the power 5, then we can see that time t is going to scale as L to the power minus 0.5. Okay. So what it means is that if you are talking about two different motors, one is smaller in size, a small size motor will reach the maximum speed, the top speed faster as compared to a larger motor. So here we have different forces, the intermolecular van der Waals force will scale as L to the power minus 7, the capillary force scales as L, and the electrostatic force scales as L square, and the force of gravity scales as L to the power 3, the magnetic force without an exterior field scales as L to the power 4, and the centrifugal force also scales as L to the power 4. Now with that we move on and talk about how the scaling is going to work for different microsystems. The first example that we are going to consider is going to be a parallel plate actuator, where we would have two parallel plates, and since there will be oppositely charged, there is going to be a force that is going to exist between them, okay, and that can actuate the two parallel plate in a fashion that can be used for different microsystems applications. So we are going to look at parallel plate actuator, capacitor, and we will look at how the scaling law is going to work. Okay. So we can draw two parallel plates here. This is one plate and this is another plate. So let us consider this is y, this is x, sorry, this is z, and this is x, and we say this is plate 1 and this is plate 2, this is negatively charged plates. So we have negative charges here, is positive, okay. So the electric field is going to be in this direction, E, and the separation distance between the plates, let us say it is D, and the length of the plate is A, and width is B, okay. So the plate area is A into B, okay. So we can write the surface charge density, sigma as total charge over area of cross section, right, and if the plates are at potential phi 1 and phi 2, the voltage across the capacitor can be written as phi 1 minus phi 2, okay. And so V can be written as E into D. E is the electric field, okay, this is electric field, and D is the separation distance. So we can write this as sigma over epsilon. So this is, we can write electric field as sigma charge density over epsilon, right, into D. So we can write V equal to sigma over we can write d over epsilon, and sigma we can write q over a. So, q over a. So, we can write q equal to C into V, where C is the capacitance which is given by epsilon A over D, okay, epsilon A over D. So, we can find the energy stored in the capacitor. Energy stored is going to be U equal to half q square over C, half C V square. Now, since these two plates are oppositely charged, there is going to be a force F between them, and if you are going to move one of the plates by a distance delta z, then we would need an energy which is F into delta z. So, the force between the plates, let us call it F, and to increase spacing by delta z, the energy required would be F into delta z. So, let us call this delta W as the energy required. Now, the corresponding change in the energy stored. So, change in stored energy we can find delta U will be half q square into change in the capacitance, because the total charge is going to remain unchanged. So, the moving the plates would change the capacitance. So, this is going to be half q square into delta z over epsilon A, right. So, this is, let us call this as equation 2, call this as equation 1. Now, if we equate 1 and 2, we get F equal to q square over 2 epsilon A, which will be sigma square A over 2 epsilon. So, for a constant charge density, the force between the two plates is going to scale as L square, okay. So, this is the electrostatic force. So, this is the electrostatic force which is going to vary as L square. Now, the inertia force scales as L to the power cube Fi. So, if we take a ratio between F electrostatic over F inertia, it is going to scale as 1 over L, right. So, what we see here, we see that as you reduce L when you go to microsystems, then the electrostatic force is going to be more and more dominant, okay. So, that is the reason why electrostatic actuators that use parallel plate configuration are made smaller and smaller. So, if you make the electrostatic capacitor based actuators smaller, the electrostatic force is going to be dominant over the inertia force, okay. So, the sensitivity of the actuation can be enhanced. So, what we see here as L reduces, the electrostatic force goes up. Okay. So, what we learn from here is that electrostatic force becomes more dominant at micro scale. Okay. Now, if you compare how electromagnetic force is going to scale. So, the electromagnetic force, the magnetic force, electromagnetic is going to scale as L to the power 4. Okay. So, let us call this Fm. So, if you Fem, so Fem electromagnetic force divided by the inertia force is going to scale as L. So, as L reduces, electromagnetic force is going to be lesser significant, okay, less significant. So, that is the reason why electrostatic actuators are preferred in microsystems. So, electrostatic we see here that electrostatic force increases as the length scale reduces, where the electromagnetic force is reducing as length scale reduces. So, what we can conclude is that is the reason why electrostatic actuators are used in microsystems. Next, let us look at how the scaling is going to work for a thermal system. Okay. So, we are going to look at scaling in thermal systems. So, here we have heat transfer, assuming that it is by conduction. So, let us say Q transfer is going to be K A delta T over L. So, you are going to scale as K delta T into L. So, Q transfer scales as length scale. Now, if we consider volumetric heat generation, okay, heating is being done internally. So, the volumetric heat generation will be proportional to the volume of the object. So, you can write volumetric heat generation will be proportional to L to the power Q, right. So, this is volumetric heat generation. Now, if you take a ratio between Q heat transfer over Q volumetric heat generation, it is going to scale as 1 over L square, right, 1 over L square, right. So, as L reduces, the Q heat transfer divided by Q volumetric heat generation reduces, okay. Sorry, this is going to increase, okay. So, what we see here is that the microsystems are capable of handling internal heat generation in a much better way as compared to larger systems, okay. So, what we learn from here is the volumetric heat generation can can be better taken care of in miniaturized systems. Okay. So, next we consider a case where we talk about transient unsteady heat transfer. So, if you place a hot object in a cold ambient, the heat is going to be dissipated from the object to ambient. As a result, the temperature of the hot object is going to change with time, and we see by miniaturization how the heat transfer, the temperature characteristics are going to vary as we change the length scale. So, we consider dynamic heat transfer case. Here we have a hot body, let us say initially at temperature Ti, and in an ambient at T infinity. So, Ti is greater than T infinity, and the temperature of it is going to vary as T with time. Okay. So, we can write the energy balance, we can write rho density of the object into C specific heat minus dT over dt, because the temperature is going to reduce with time. So, there is a negative sign here, is going to be H A into T minus T infinity. So, you can write a solution for this. If you solve this simple differential equation, the solution can be written in this form: T minus T infinity divided by Ti minus T infinity. So, with the initial condition that temperature at time t equal to 0 is going to be Ti, right. So, T equal to 0. So, this will be e to the power minus H A over rho C V into T. Okay. So, that is how the temperature is going to vary with time. So, we can write the time constant, tau is going to be rho C V over H into A. Okay. So, you can write this as rho C over K into V divided by HL over K into L. So, this term is 1 over alpha, alpha is called thermal diffusivity, which is a property of material, and this is known as Biot number, okay, which is a constant. So, the time constant is going to vary as V over L, or it is going to vary as L square. Okay. So, what we see here is that as the system is reduced in size, as L is reduced, the time constant is going to reduce. Okay. So, this is a very important conclusion, where the length scale L reduces, the time constant reduces. So, this is the reason why we try to make the thermal sensors smaller and smaller. As the thermal sensors become smaller, because of the small length scale, the time constant is going to be reduced, for which if you expose a sensor to an ambient, it is going to be very quickly attain the ambient temperature and read it accurately. Okay. So, this is used to design thermal sensors. Okay. Now let us look at another microsystem, how the evaporation of the droplet is going to scale with the length scale. Okay. So we look at evaporation of droplets how the scaling is going to work. So we know that the evaporation of the droplets is going to follow what is called d square law. Okay. So evaporation of droplet I am going to use d square law. Okay. What it means is that d square equal to d0 square minus beta t. Okay. So let us say we have a droplet. So this is the initial size of a droplet and this is droplet size, drop size at time t, and so this is time, and beta is a constant that is independent of droplet size So if you want to find the time scale at which the droplets would disappear, okay. So in that case you can say that the time constant will be d0 square over beta. Okay. So the time constant is going to scale as L square, right. So what it means is that as L is going to reduce, the time constant is also going to reduce. So what we see here is that miniaturization favors droplet evaporation, right. Miniaturization favors droplet evaporation. As the droplet size is smaller and smaller, it is going to evaporate very quickly. Okay. And this is going to be important in case of applications where we are talking about pulmonary drug delivery, for example. So there we generate small size droplets, a plume of small size droplets, and we have to, when you design a system, we have to understand that if the droplet size is going to be smaller, it is going to evaporate very quickly following d square law. Okay. So next we move on and talk about the scaling in fluidics. So we talk about scaling effects in fluidics. So here we consider a straight channel of diameter d, let us say this is d and the velocity is u, let us say delta x is the length of the channel. Okay. So we know that in case of laminar flow through a channel or a tube, we can apply the Hagen-Pauli law. So if you apply the Hagen-Pauli law, right, we can write delta P over delta x is going to be 32 eta u over d square. So, here delta P is the pressure drop, okay. Delta x is the length of the tube, eta is viscosity, dynamic viscosity, u is the average velocity, and d is the diameter. So, what we see here is that the pressure drop is scaling as 1 over L square, okay. And so, now from here we can rearrange the term to write u equal to delta P over delta x into d square by 32 eta, okay. So, this is what we can write. Now, we can write the expression for the flow rate. Q will be the area of cross section, which is pi d square over 4 into u, which will be delta P over delta x into 1 over 128 eta into delta P over into pi d 4, okay. So, what we see here is that the flow rate will scale as L to the power 4, right. Now, if we reduce the diameter of the channel by, let us say 10 times, okay. So, if d is reduced 10 times, then what is going to happen? The delta P is going to increase by 10 to the power 4 times, okay. So, if the channel is going to reduce 10 times, the delta P is going to increase by 10 to the power 4 times, the pressure drop is going to increase, which is an undesirable effect. On the other hand, the Q is going to reduce by 10 to the power 2 times, okay, right, sorry, yeah, this is 10 to the power 2 times, because pressure scales as L square, right, delta P scales as L square. So, this is going to reduce 100 times as L is reduced 10 times, and Q delta P is going to increase by 100 times when D is reduced 10 times, and the flow rate is going to reduce by 10 to the power 4 times. So, both effects are undesirable effects. When you are talking about scaling down the size of a microchannel, okay, if you scale it down by 10 times, the pressure drop across the channel is going to increase by 100 times, and the flow rate across the channel is going to reduce by 10 to the power 4 times, okay. So, scaling down is not helping the pressure drop or the flow rate, okay, and this is the case when we are talking about pressure driven flow. Pressure driven flow, it is basically a volume force, okay. So, at micro scale the volume effects are very small, whereas the surface effects are dominant. So rather than using Poiseuille flow, pressure driven flow at micro scale, things like electroosmotic best flow or piezoelectric best flow are used, because these are surface driven forces. At micro scale these effects become more and more dominant. So because of this reason, pressure driven flows are not favored at micro scale, and electroosmotic flow piezoelectric or acoustic driven flow. So these are used. This is because these flows are driven by surface forces. So this will require alternate pumping techniques at micro scale in micro channel. Okay. So to drive fluid in micro channels, instead of going for pressure driven flows, we would be using electroosmotic best flows, acoustic flows, piezoelectric driven flows, which we will be discussing in the later part of the course. Okay. So with that let us stop here.